On the first day of data science, my model gave to me a one-hot encoder term.
A one-hot encoder term is a way to represent categorical data in regression or machine learning algorithms. So say we wanted to know what kind of effect Monday has on the model, we can make a variable called isMonday that is a 1 if today is a Monday and a 0 if not. If the model comes out with a large coefficient, that means Mondays have a really big effect on the model. Garfield, is that you?
On the second day of data science, my model gave to me a binary tree.
Let's talk about binary trees. Real simple. Imagine a family tree, but for data. You've got at the top the first point, or the root, and from the root it stems off into two branches, the left branch and the right branch. If you move further down the tree, some branches keep splitting and some branches come to a complete stop. When a branch stops, well, that's called a leaf node, and that's where the path ends. It's basically a game of higher and lower. Each step you take cuts the choices by half. Why do data scientists love binary trees? Well, it organises information into a clean hierarchy format, making searching and sorting super fast. Decision trees in machine learning are basically binary trees, and even in finance we use binary trees to price options. Binary trees show up everywhere in data science. They're even a little gift to put into your stocking.
On the third day of data science, my model gave to me 3 data splits.
For this one, I'm talking about splitting your data into 3 parts to be able to train your model without overfitting. The 3 splits are train, test, and validate. Train is what you use to teach your model, much like how ChatGPT gorged on the entirety of the web before its release. You can use this data to teach patterns and relationships. After training, you can adjust the model's parameters using the fresh validation set of data that it hasn't seen before to really fine-tune those parameters. For example, ChatGPT sometimes gets adjusted to sound a little bit more sycophantic. The test data is your final unbiased evaluation to see how your model performs on new data that it hasn't seen at all. This is what you need to know if your model generalizes beyond the data that it was trained for.
On the 4th day of data science, my model gave to me 4 quartiles plotting.
Ever wondered how we find the true middle of a data set? We use quartiles, basically splitting the numbers into 4 equal parts. Q1 equals 25%, Q2 is 50%, Q3 is 75%, and Q4 makes up the rest. Interquartile range, or IQR, is basically Q3 minus Q1. Think wages in a company. If the IQR is low, then it shows that the employees are on a similar wage. If the IQR is high, then it shows that some people are earning the big bucks. We like the IQR because it ignores the extremes. It removes the 1-day-a-week worker and the CEO earning a huge salary, so we can get a clearer understanding of what's going on.
On the 5th day of data science, my model gave to me p-value less than 5.
Often when we're dealing with data, we need to be able to tell whether the things we notice are a meaningful thing or not. So we create a null hypothesis, which says that there is no meaningful effect or a relationship. We might say, for example, that shoe size and height have no relationship whatsoever. The alternative hypothesis says that there is indeed a relationship. So in this case, we'll say that yes, height and feet size do correlate with each other. We then use data to find out if we can reject our null hypothesis and say, yes indeed, taller people have bigger feet. Usually the threshold for deciding whether the evidence is strong enough to reject the null hypothesis or not is given by the p-value, and a really common threshold for this is given by 0.05, which means technically I should have sung p-value less than 5%, but I don't care.
On the 6th day of data science, my model gave to me 6 degrees of separation.
Okay, so this one's easy to explain. Even I understood this one.
Don't sell yourself short, you are brilliant, my love.
Thanks, Lee. I'll pay you later. So, the idea of this one is that we are all connected to each other by 6 social connections. Ever been in a room where you overhear a conversation and someone's talking of a friend of a friend of your friend, and you're sat there thinking, hold on a second, I know that person, and just what a small world we live in? Well, that's exactly this. It shows just how connected us humans are globally. And we may just be closer to interacting with those celebrity crushes than we might just think. We can even look at illnesses throughout the years. I mean, COVID being the most recent. And using the rule of 6, models just how easily diseases can be spread through the population. And how does this relate to data science, I hear you ask? Well, think of it like this. Data scientists take those friend of a friend connections and work out who knows who, what information is being spread, and what similarities these people have. And based on those, they can create something using our small world to make us understand and use, like our next connection. LinkedIn and Facebook use this all the time, popping up with people you may know and what's a business without networking. Even subscription channels are doing this. Netflix creates a whole list on future watches based on previous watches. And even whilst you're watching this video, YouTube's behind the scenes creating an algorithm to come back and watch our next video. So why not save it the bother and hit like and subscribe.
On the 7th day of data science, my model gave to me 7 housebound frauds.
Alright, so we're getting a little bit niche with this one, but you know us, we like to take data science to the real world. So we're going to talk about something very specific here, something called Benford's law. This is basically the observation that in real-world sets of data, the leading digit, the first numbers, tend to be pretty low, and that's generally a side effect from things counting up. So unsurprisingly, 1 appears as the first digit about 30% of the time, and 9, that shows up less than 5% of the time, whereas if these numbers were normally distributed, every single number would show up around 11% of the time. Where this is used in fraud detection is because humans aren't uniform in the way that they guess numbers, and if asked to give a number, most people tend to give the number 7 at a much higher rate than would be implied by either uniform distribution or Benford's law. So, looking for significantly higher appearances of the number 7 might be an indication that something's been faked and maybe some fraud is going on.
On the 8th day of data science, my model gave to me 8 nearest neighbours. Sometimes we want to make a decision around what's happening on a specific data point. And to do that, we need to look at its 8 nearest neighbours. Imagine you've just moved into a high-rise building and you're on the 56th floor and you hear a strange noise. We're not going to suddenly mooch around the first floor to find out where the noise is coming from, are you? You're going to look at your closest flats, the ones next door, above, below, across the hall, and even your diagonals. And this is what data scientists do. We can label a data point based on the labels of its closest neighbours. We can make recommendations like YouTube does, and even spot those outliers, the ones that have no neighbours at all.
On the 9th day of data science, my model gave to me 99% confidence.
2, 1.
Oh my gosh, Nintendo Switch 2! I was so confident I was going to get this right that I left my script across the other side of the room, and turns out I needed it. Sometimes we say things like, children play games between 2 to 4 hours with a 99% confidence level. What we're saying is if we repeated this analysis on children playing video games 100 times, then the true mean number of hours spent would lie in the confidence interval given by the model 99 times. So we're 99% confident that the average time children spend playing games is within the confidence level as given by the model. Anyway, enough of this.
On the 10th day of data science, my model gave to me 10 top 10 lists. Everyone's heard of Top of the Pops, right? Or am I showing my age? When I think top 10, I think music chart. Instead of listening to every song ever made, we narrow it down to the top 10. Radio stations do this every week, making sure that their fave artist hits that #1 spot. Why is this useful? Well, it highlights what actually matters. Businesses can use their own top 10 to show the areas that really need their attention, which metrics to track and which products and features are performing the best. It stops you from drowning in data and shows you what really counts.
On the 11th day of data science, my model gave to me 11 husband things.
Wait, what does that mean? I'm sorry, hang on. Graham?
Yeah.
Graham, this one's too nerdy even for me. You put this on. You're gonna do this?
Okay.
I'm going home. See you later.
Okie dokie. So maybe you've noticed that on the back of most books is a number. It's called an ISBN. And if you've looked very closely at them, maybe you've noticed that just once in a while it ends in an X for no obvious reason. And I want to talk about why. Because first of all, if you have noticed that, congratulations, that's 3 points towards your autism diagnosis. And second of all, you've probably just rediscovered modular arithmetic. So what do I mean by that? So ISBNs are often typed by hand. And so the last digit is there as what's called a check digit to detect typos in that number. And the way we do that is a simple mathematical sum of the other digits, add them up, and take the last digit of that sum. However, it turns out that doing that sum using base 10 arithmetic is not ideal, and that's to do with the fact that 10 is not a prime number. And so we do the sum in base 11 arithmetic. And that leaves us with just one final problem, and that is what happens if the remainder happens to be a 10, given there's no decimal digit for 10. And so what happens is we took the Roman numeral X to mean 10.
On the 12th day of data science, my model gave to me 12 seasonal forecasts. Seasonal forecast, the fortune teller of data science. It simply uses past data to predict future outcomes. Let's take Christmas shopping. At Harrods, every December sales jump. Why? Well, Christmas, duh. More gifts, more online shopping, and plenty of last-minute shoppers coming out on the 24th. Men, I'm looking at you. From that pattern, we can predict what we need. More stock, more staff, and more prep. That's why Christmas temps exist. And it's not just Christmas, it's strawberries at Wimbledon or McDonald's stocking up when the kids finish early. Anything driven by the calendar fits. We look at the past, pick out the present trends, and predict the future. Last one.
12 seasonal forecast, 11 instant thing, 10 top 10 list, 9% confidence, 8 nearest neighbours, 7 house spot fraud, 6 feet separation, p-value less than 5, 4 quartile spotting, 3 data splits, a binary tree, and 1 hot encoder.
Merry Christmas, everyone!